Hi, everyone. Welcome to PAVE's 110th virtual panel. My name is Tara Andringa, and I'm the Executive Director of PAVE. A lot of people, understandably, have concerns about the idea of getting in a robot-driven car. And so what we like to do is sort of explain how the technology actually works. And we have two amazing experts joining us today to talk us through that. They're both CEOs of PAVE member companies. Aaron Nathan, who's the CEO, CTO, and founder of Point One Navigation, and is also just coming off of paternity leave. So impressive picture of wide awake. And Dr. Anuja Sonalker, who is the CEO and founder of Steer. Well, thank you both for joining us today.
Pleasure to be here.
We are super excited for this conversation. We also got a bunch of great questions from the audience. We'll try to weave in as many of those as possible. Aaron, we'll start with you. And I will admit that in preparing for this panel this week, I learned something myself. Navigation is obviously a really important part of getting AVs to work. I'm hoping that you can provide an overview of Point One.
Absolutely. Again, thanks for having me today and letting me talk through navigation and why we think it's so important here. When we talk about absolute navigation, what we're talking about is putting yourself in a place that everyone agrees is the same place in the world. And that sounds kind of like an obvious thing, like, hey, this is a house that's at the intersection of Main and Fifth. But the reality is that a lot of early autonomous vehicles and types of things that were done with advanced driver assistance systems, like the types of vehicles in production today, they use something called relative navigation, where they're actually just operating relative to something that they're able to see, like the lane lines that are pointed in front of the car. Or in a lot of other AVs, they may be only operating relative to a map. They don't actually know the latitudes and the longitudes of the points that they're driving in. On the flip side, absolute navigation is something that is tied to this kind of global coordinate system. And the real power of this and why it's so important is that this allows all the vehicles to kind of operate in the same frame. And then they can even communicate amongst each other to say, hey, I'm about to slam hard on the brakes because there's an accident in front of me. And then all the vehicles behind actually will know exactly where that car is and if they need to take action as well. And so there's a lot of advantages to operating in this kind of absolute navigation frame. And that's what Point One really does. We make it easy for developers of autonomous vehicles, robotic systems, ADAS systems to be able to operate in this absolute frame and do so quickly, economically, and most importantly, safely. And so, in terms of your phone can do some of these things, but like super low resolution. What you need for any kind of a safety system is that you need assurance that it works and it needs to be extremely accurate. And so Point One actually gets to about 10 centimeter, that's the Point One in our name, level resolution for us to be able to tell you where you are in this absolute frame. Tara, I think you're muted, sorry.
Thank you. Sorry about that. Anuja, similarly, I'm hoping that you can provide an overview of Steer, from having a car be able to park itself to being able to drive, automate many applications that are useful to all drivers. Can you explain what it is that you all do?
Sure, thank you. So Steer builds low-speed autonomous applications. We started certainly from parking and being able to park your car in parking lots. But very quickly, about 2 years ago, we expanded into airports and parking in airports and then rental car fleets. And then from there on, it was a fleet market. So fleets require efficiency, they require safety, they require doing the same operations over and over again inside of parking lots or yards or depots. And so we ended up expanding, and it's truly a low speed autonomous application in private geofence spaces to serve an end customer and their use case. So it's sort of bespoke in that sense, but typically we operate in yards, depots, dispatch centers, facilities, and parking lots, campuses, etc. Those kind of environments where we are doing the same repeat activity over and over again, whether it's automated charging, automated parking, whether it's bus washing, whether it's tactical operations. So we have government military programs as well, doing similar operations there. So that's basically, in a nutshell, what STEER does.
I have one quick question. I looked on your website, you talk about both L2 parking and L4 parking. Can you talk about how those are different? Does the driver actually play a role in L2 parking?
Thanks for pointing that out. It's a very important distinction. And L2 parking and L4 parking, the major difference between them is the driver, how much human assistance and how much human in the loop is involved. So L2, think of it as remote parking. So it's human guided. The vehicle is doing the maneuvers, the vehicle is doing what it's supposed to do, but it's doing it on cue. The human is the one asking it to do what it's doing, its activities. L4 is where the human just gives it outcomes and says, go park for me, right? And then the vehicle is going to figure out everything. Where is the nearest parking? How does it need to navigate there? Where is there an open spot? And how do I fit in that open spot? And then maneuver itself in the spot, and then let the human know that, okay, job is all done. So that's the level. So how much you hand hold the system is different. So in level 2, you're holding more. In level 4, you're leaning back more and letting the system do its job. So that's the difference. And same L2, L4, it applies to fleets also. So it's how much is human guided, so remote operation versus fully automated inside that.
Great, thank you. And then Erin, I want to go back. You talked about obviously the importance of absolute navigation. And a lot of companies talk about this concept of sensor fusion and how the collective input of all these sensors is important. I'm curious if you can talk a little bit about how satellite navigation works with other sensors like cameras and LiDAR. How do these all integrate, and what are the important roles that each of those plays?
Yeah, so it's a great question. Like, satellites are very unique because they provide something that literally no other sensor can, which is actually where you are on Earth. Cameras, LiDARs, IMUs, these sensors are obviously very prevalent on AVs and even production cars now, but they can only tell you where you are, again, relative to things. Now, we talked earlier, like, there's a lot of benefits to having this concept of absolute, but the problem with satellites is that you have to go and see them. And so we've all experienced, trying to get an Uber in the city and your phone doesn't quite work so well when you're in downtown Manhattan. That's because you can't really see these satellites. And so how do you basically solve for making this absolute frame available when you can't see satellites? And the answer is with sensor fusion. And so effectively what that means is that you're blending the information that you get from all of these raw sensors to come up with something that's a more high-level concept like location. Basically, if you think of an IMU as an example, an IMU is a sensor that tells you how you're rotating and how you're accelerating. And if I take that information, that tells me something about my location. So there are sophisticated methods that you can use to implement blending that IMU with the satellite data and incorporating other information like the camera and seeing how the picture is moving through the scene, putting that all together and then using it to literally cross-check and then in the most advanced systems cross-calibrate all of those different sensors. The high-level construct of this is that it helps you be immune to the failure modes associated with any particular sensor. My very firm belief, and I think many in the kind of autonomous vehicle world would believe this, there is no sensor that is immune to failure. And so the best that we can do is make it so that we have redundancies and can detect and ideally compensate for those failures in real time. And that's ultimately the job of sensor fusion, is to detect when a sensor is operating outside of maybe its design domain, or making it so that that sensor has failed, A, knowing that it happened, and then B, hopefully being able to rectify the data at least long enough for you to get to a safe condition. And that's really the whole point of what we do with location sensor fusion and what everyone is trying to do with sensor fusion across perception, navigation, and all the other tasks in the autonomous vehicle.
Great, interesting. Thank you so much. And Anuj, I want to go back a little bit to the parking idea. I think this is something everyone can relate to, is having parking a car that can park itself or help with parking. But I'm curious about how that how you fit that in with, whenever we talk about, AV deployments, we talk a lot about the ODD, or the operational design domain. And I'm curious how that fits in with parking. Does every single parking spot need to be mapped, or does the technology use different sensors for navigating parking?
So see, the concept of ODD is very important to
Mm.
Steer's technology, as it would be for all special purpose AV technologies, right? Um, Steer is carefully built to operate in specialized environments in private sites, whether it's parking lots or garages or rental car facilities, depots, yards, motor pool ops, etc. um, you don't necessarily need to have to pick the end point, like the parking spot, and mark each parking spot. You need to identify those zones. So this is where parking can be done, this is where driving is done, this is, things like that. And then it is, because it's level 4, that means it is dynamic enough and understands the situation and the environment around it, that it can sense this is an open parking spot, this is potentially where I can park, potentially because I need to make sure that that car fits in that size, right? So whether you're a Hummer or you're a Prius, your space requirements are different. So to be able to make that expert judgment and then only maneuver into that spot. So all of that. So there is some dynamicity even in parking lots. There is a lot of dynamic things going on. Different vehicles are traveling in all kinds of directions, not like on the highway that everybody's aligned and going in one direction. So there are all these different things going on. But to the point, what we do is you create a, since you talked about ODDs, you distill a macro ODD from there. So based on what I described, the technology and all these different types of applications, you can distill a macro ODD and say low speed, private, geofenced, non-public facing. That becomes your macro ODD. And then you can refine it to a micro ODD, which are operational requirements of the customer. The end use, is it parking? Is it something else? Is it they have a workflow and they have an operational workflow? Do you need to absorb that workflow in, or do you need to create new operational workflows that are hybridized, that are designed to absorb the benefits of the automation? So that merge defines not only the AV operation, but also the efficiency, the safety case, the ROI, savings, interoperability, all of that. So it becomes very important to understand your ODD, do a discovery of that, and then your fitment in there, and then the edge cases that you need to absorb in there. So parking is an example of the same thing. We will not go and map each and every parking spot because it's not feasible. Like today, a parking spot is taken, tomorrow it may not be taken. And so same day your vehicle comes around, same time next day somebody else may have taken the spot. So that's not really feasible. So you have to adjust to the workflow and you have to absorb that in.
Interesting. Exactly. Thank you. Aaron, wanted to go to a question we got from the audience about validation. And they asked, what criteria can regulators use to validate sensors? And then more broadly, can you describe your approach to system validation?
Yeah, validation is, it's an incredibly complex topic because there's validation at multiple levels within AVs, which in and of themselves are multi-layered systems. So like if we were to just decompose the location navigation task as one item, you look at each of the sensors that we talked about, an IMU, a camera, a GPS receiver, all of those have to have a validation, and each one of those are going to be very specific to the domain of that sensor. An inertial unit may have to be tested over different temperature ranges, over different vibe and shock profiles. A GPS receiver has to be tested in different sky conditions and under different RF levels. And so the reality is that you have to first decompose the problem into all the different pieces that you have. And you have to be able to make a holistic assumption around, okay, what needs to function at the base layer so I can guarantee the actual function of my overall system. And so when we talk about system validation, it is normal that you will get into situations where certain sensors don't work. If I take my AV and I drive it into Manhattan, the GPS receiver will not be able to see satellites like we talked about, but that's expected behavior. The key here is, how do you make it so that the overall system performance is still within the specification for all the different ODDs that you're trying to certify that for? The overall answer to this is a blend of simulation, for sure, and then real world testing. Now, real world testing is interesting because it actually has two different dimensions. Of course, you can record data and test it and make sure that what happened in the real-time system happened in your playback system. But once you do that, you can actually now start to augment what happened in the real-time system. So for instance, simulate that the wheel speed sensor went crazy and started doubling the wheel speeds, or that all of a sudden the GPS dropped out, or your cellular connection broke. And so this data augmentation is actually one of the key things that we do at Point One. We're able to take one like data set, one drive, and then we can generate probably a combination of easily in the 60s, 70s different potential failures that can happen in that system, and then just check the response. The last piece of this is that validation doesn't happen once. Every time you make a change, whether it's on the sensor side or changing the actual algorithm that's doing the sensor fusion, you need to revalidate. And so it's a continuous process that, frankly, we borrow a lot from what people have done in the software world for ages to do their regression testing on software. But we do that as well on a performance level for what the algorithm's robustness to different failure conditions are. And I think, frankly, there is no other way to do this, to try to do all real-time testing. I think in the early days of AVs, we saw that it just doesn't scale.
Yeah.
And that's why you need this data augmentation, you need simulation, and you still need real-world testing.
For sure. And actually, I wanted to kind of stick with that issue a little bit. We actually got a question from the audience about simulation. Anuja wanted to know, how do you use AV simulation in your work? And then asked, do you use it for planning and control testing, full end-to-end sensor simulation, scenario testing, or something else?
All of the above. So we have simulated every layer of the AV stack, right? So the AV layers are very complex. They are verticals, horizontals. They are pretty complex out there. And so we've simulated every layer of the stack, and in each layer we can simulate perturbations that may be caused by the layer above it or below it. So if the sensors are reporting something out of bounds to the planner, then how does that react? And all the various combinations of data that it needs to be responsive to. Or there's a perturbation from the above layer, from mission control to low level control, etc. So the advantage of using a simulation here is that you can now simulate activity that is otherwise very hard to trigger by practical use cases from the outside, right? So if you take from a vehicle standpoint and trigger using use cases, you can't necessarily trigger all those many states that the software should be exercised. And so you may never get to exercise certain states properly. So therefore, there is value to using simulation, and especially breaking it up, and each block by block, you're simulating the layers above and below it and the layer that you're actually testing. And one can ask, okay, why would you want to do that if it's not really a use case that you will see, and if those certain states are artificial states that may never ever get triggered in the real world, why would you want to simulate that? Well, two reasons, right? One is it is to trigger the fail safety mechanisms and make sure that fail safety mechanisms are being triggered when certain triggers are seen, and so you have to exercise that. And the second one is intrusion detection mechanisms to see that they are working properly or not. Because again, to the point where if that's not a real life situation, then some of those states may be observed, a hacker or a penetration can occur, and then they are artificially creating that environment inside your vehicle in order to exercise certain states. So you want to make sure that you are triggering the right mechanisms and you're able to recognize that. So that's the value. That's the true value of simulation, is it has its place in the real world. And then there is no substitute for on-road testing, which is also a big part of our testing and our deployment plans. So we'll put the vehicles to actual test scenarios, and several hundreds of these within small confined ODDs that we are deploying in order to monitor, in order to measure behaviors and performance and look for outliers and edge cases. And even that gets fed back to the simulator. So we want to make sure that your simulation is as close to reality as possible. So definitely, it's very important. Both worlds are very important.
Absolutely. Interesting. Aaron, you've made a couple of references to kind of, if you're in the middle of Manhattan, and it's interesting. We actually got an audience question kind of about that. We've all had the experience. You're driving along, your cell phone, your call is dropped, or you lose connection. And I kind of wanted to just dig a little deeper. What happens if the vehicle loses connection or there's a break in satellite communication? I know you talked about redundancies, but how do you ensure that the system still works? And then the audience question that I sort of feel like fits into this is how can navigation be perfected in areas with urban canyons such as Midtown Manhattan? Just wonder if you can dig a little deeper on that.
Yeah, absolutely. I mean, so, the communication requirements of AVs as a holistic system, I mean, are very complex. And a lot of those actually are driven for the last kind of fault tree that we were talking about earlier is, okay, the human operator in the call center or something more or less has to tell the vehicle how to get unstuck. That, as far as I know, every AV company that's out there today has something like this. And that means that they have to be ready to do that. And so if they lose their cellular communication, they have to stop. They have no other option because otherwise it would be unsafe to continue. That has nothing to do with navigation, to be clear. That's just the design of those AVs. But from the navigation task, the way our system works is that we are able to basically in real time download a lot of information that tells us what's wrong with GPS signals, et cetera, to amplify their accuracy by about 100 times. And we do use cellular as one way to do that. The way that we've made that robust is we've actually developed additional communication strategies. So we actually rent time on a satellite to be able to broadcast the data in parallel to having it come over a cellular modem. And so there are ways to increase the redundancy on the comlink path and make it so that the system is actually highly available. And I think this is a part of the AV design system is not just what's on the car. There's a lot of infrastructure that's being built behind the scenes that is maybe less obvious, but is, I would argue, as or more important. And I think we're seeing a lot of this too with the latest 5G specifications, thinking about how to prioritize traffic for these critical systems, whether you're, an AV operator or, a first responder even. And so anyway, I think there's a lot of different things that happen at a system level to make those redundancies possible. Now, on top of this, we have a lot of customers who are not autonomous vehicles yet, but are still in like the ADAS, the advanced driver assistance. And in those cases, it's more about can you get to safety? And so you can now start to think about designing, again, sensor fusion algorithms that basically buy you enough time to get to a safe state. So if I'm driving 60 miles an hour, how long does it take for me to navigate from the left lane to pull over into the shoulder? And so you can design basically your safety case around those kinds of maneuvers. And then that becomes the requirement that drives, okay, how good does your navigation really need to be in these failure modes? Now, I think this is kind of one of the coolest things about autonomous vehicles in this world is we're spending, I would say, more time on these like edge cases than we are in the like 95% of driving a car. And I can tell you just even from the old days of the DARPA Grand Challenge, like we solved, I would say, the 75% of driving an autonomous car 15, 20 years ago. It's working on those edge conditions is incredibly difficult. And that's really what a lot of the latest technologies are so focused on solving.
Sure. I'm going to see if we can fit in two more questions in less 4 minutes. Anuja, when we do a lot at PAVE, we do quite a bit of polling of public, kind of what people's concerns are about, the idea of autonomous technology. And one thing that people bring up is cybersecurity. Both, and I think it has two aspects. One is like kind of personal data, and also, how do you make sure like a hostile government or something isn't taking over your car? I think of the 1980s movie War Games. But how do you ensure that your system isn't going to be hacked? What precautions do you take, or how would you assure the public about that?
Very loaded question. Very loaded. So
And you have 30 seconds to answer. I'm kidding.
Let's say the first thing, let's accept that any system can eventually be hacked given sufficient time, resources, knowledge, and access. Okay, so that there is no system that cannot be hacked. The name of the game is to ensure that the system is hardened to the point where it is not feasible or practical for someone to hack the system with whatever within the limited window of opportunity that they may have, whatever the size of that opportunity. So that's the name of the game. And the most generic advice I can give, and the audience is more than welcome to tap me for any, specific advice for their cases. I'm more than happy to give that. But the most generic advice is to build your security in a distributed manner. I'm a distributed system security person, and my mind first goes to distribute things. You break things up, right? You distribute your assets. Imagine your AV not as one asset, but a bunch of assets. So you zoom in, let's start zooming in, and then we'll zoom out to the solutions in zoomed out layers. So you look at your AV as not one asset, but as a bunch of assets. You separate them all logically, and you apply protection mechanisms to them that are commensurate with their value. So whatever is the most valuable asset, you put more protection. Whatever is less valuable, you put, lesser protection, and so forth. So you balance it out accordingly. Then zoom out. Now you add an overall mechanism to monitor the whole thing, right? And then zoom out further, and now you need to you have solutions to defend yourself if you catch something. So if you monitor and you catch something, what are you going to do about it? So you want to have some solutions in place to either deter, to mitigate, or to escalate to a human or a network operations center somewhere and point to them that, okay, there's an issue here and I figured it out, and now your job to figure out the outcome. Any of those are possible, right? Then you further zoom out. You need an overall plan to address issues over time that one would expect over time, because over time adversaries get stronger and vehicles just age, right? So and you can update them, you can do over the air updates and all that good stuff, until you can't do that anymore, because the hardware cannot keep up anymore. That's it. You've hit the limits of how much updating you can do and how much more can go on the systems. So you have to have other mechanisms, right? So therefore, all these layers of cybersecurity that you apply will defend you. So there is not one open attack surface. You have sort of a maze, and the adversary has to sort of windingly go through that maze to get to the actual asset that you're trying to defend, whether it's your personally identifiable information of people, so privacy is the issue, or whether it's car data, whether it's, control of the ECUs and control of your vehicle, etc. Any of these, like you break them up and you identify them as logical assets, and you apply protection mechanisms accordingly. And the last thing I'll say about that is redundancy, right? So agree with Aaron 100% on redundancy. Redundancy should not be sensor based from a cybersecurity perspective, right? You don't create redundant sensors as a backup for a sensor exactly, or an actuator. You don't create that, but you do redundancy capability based. So you don't create a redundant sensor for every sensor, you create redundant sensing. And the difference is that, for example, positioning, right? If you have a RTK GPS based positioning sensor, its backup redundant sensor is not necessarily another RTK GPS based redundant sensor. It could be a UWB based sensor. It is giving you positioning, but from a completely different modality. So that way, if you're attacked, everything doesn't go down at the same time, right? You need a very different type of attack to attack both of them.
Fascinating. That makes a lot of sense. Just want to sneak in one last question. Aaron, I'll ask you, we always get a lot of public sector officials on our who tune into our panels. Curious what input you would give to regulators from your vantage point in the industry. What regulation or policies do you think is the most important thing for the AV sector to advance and flourish?
Yeah, I mean, I'm a big believer in transparency. I think that's how you get the trust of public, and frankly, it ultimately makes it so that there is data that people and experts can actually look at. And I would say that the more transparent the organizations can be, the better. I would certainly caution any regulator about having large blanket things like prescribing how tests are implemented, or necessarily needing to have even human operators in every vehicle, because it'll ultimately I think stymie the innovation that we need, which is to be able to actually get to the point where these things are completely tested. As we said before, there is just no substitute for the real world. Simulation is an absolute requirement, but it is nothing is as complex as the world we live in. And so there is an absolute need for us to have transparency. I think regulators can think about what elements and standards we want for that transparency. And I think that would be a great place for there to be some discussion with the companies leading in this space. But yeah, I think these kind of blanket ideas of eliminating, different aspects of how we innovate are very risky, especially as we're in a race for innovation in the sector.
Great thoughts. And on that, we've run out of time, sadly. Thank you both, Aaron and Anuja, for joining us today. Really great conversation. And thank you to the audience for joining us this afternoon. And you can get more information on our website, pavecampaign.org. Thank you all, and we'll see you next time.
Thank you so much.
Thank you. Bye.